Hello everyone. Today we are going to talk about exponential growth and decay. So we'll start with a little preview of what is exponential growth and decay, from which kind of problems it appears in nature, like physics, biology, other sciences. So in many natural phenomena, quantities grow or decay at a rate proportional to their size. Uh, Sounds a little bit vague, like what is rate of growth and how it's proportional to size and why. Actually, I'm going to give a very kind of basic example of what is what and what is size and what is rate. Imagine that we have a couple of people and we kind of consider that couple can have one child over a year. So we have two people. I'm going to draw them as circles, and I'm going to draw the child as a green circle. And imagine that this is kind of one household or one little tiny village. Now let's imagine that we have another household and there are like four people or two couple of people, let's say, not just four arbitrary people. Let's say two. I'm going to just, maybe it's not a good idea to label them as people, but maybe it's better to label them as just kind of two objects which are reproducing. Let me, somehow I cannot change my color. Maybe my pen is not working. Okay. Okay, I'll get blue again. So imagine that we have two couples. The different village, different household. And again, the time is 1 year. I'm going to label this as delta t. Delta t is like the time period we are considering our kind of villages. Delta t. So what we have? What is population here? Population here is 2, right? 2 people. What is a change of population over 1 year? Change means that if you take the final population and subtract the initial population, delta population. Well, delta population here is 1, right? 1 extra person. Now let's talk about this size. What is total population here? Population here is 4. What is change of population? Again, that's a hypothetical case. Change of population is 2, right? And the period is same, like 1 year. What is a rate of change? Rate of change when you divide change over the time, like how many more people you are going to get over 1 year. Rate of population. So I'm going to divide over delta t over here, and that's going to be the rate. In our case, because delta t is 1 year, I'm going to just divide by 1 here and divide by 1 here. So that's a rate of population. So in this case, I'm going to label rate is equal to 1. And in this case, rate 2 over 1 is equal to 2. We see that the rate is kind of proportional. Like if you just look at these numbers 2 and 1, it's not like any proportionality. But if you compare with two other numbers, so population equals 2, rate equals 1, right? And when population equals 4, rate equals 2. So it looks like you double the population and the rate double too. So we can say that in general, the population is proportional to the rate of growth. Rate. Or in our case, if you want to write down equation, you can write down that instead of rate, which is delta p over delta t, in terms of calculus, it's what? Delta p over delta t as a limit is going to make dp over dt, which is actually a derivative of p, right? So what we have? We have that population is proportional to the derivative of the same population. And both are functions of t, right? So we see that the population and the rate are proportional. Proportional means that you kind of double population and the rate is going to double too. Or not maybe double, maybe triple, but you kind of. So what I'm going to do, guys, I'm going to turn this one into a strict equation. This is proportionality. Proportionality means that can be added a constant here or a constant here to make it like into equal sign. I'm going to add a constant in front of the population. So I'm going to write down the derivative of the population equals a constant multiplied by population itself. So bigger is population, bigger is going to be the derivative, or like bigger population like over here, and we have a bigger derivative. Smaller population, smaller derivative. You see? This is called population equation, population growth law. And this is also known as differential equation of the first order, because here our unknown is not just a variable x or t, but a whole function of t, right? Uh, what uh, what is what here? Well, here is the rate of growth. This is proportionality constant, which can be different. Like in our case, this proportionality constant is like 2, but can be anything else. And sometimes this proportionality constant can be not only greater than 0, but also less than 0. When proportionality constant is greater than 0, then population is going to grow because the derivative is going to be positive, right? When some function has a positive derivative, it's growing, right? But sometimes population constant, this k constant, is going to be negative, and then population is going to decrease. Well, usually it's not like biological populations usually don't decrease, but some other populations, like for example, radioactive material population, can decrease. So we are going to call the population growth law a natural law of growth. Law of natural growth, or law of nature. Well, I would say that biological populations decay too, but supposed to be like not very good conditions for population. Usually, guys, if we kind of get away from specific letter P, which means population, we can write down this differential equation more mathematically in terms of y and t, or you can even use y and x. I'm going to keep t because t coherent with time, so I'm going to convert it into dy dt equals k y of t. So that's like in terms of y, where y can be population or can be something else. Now, guys, how do we solve usually differential equations? Well, there are many ways to solve them, but because we are not like in Math 55, we are just going to try to guess what is possible solution of this equation, which function is differentiated and kind of give you the same function, maybe with a little constant. And you probably recall that we just learned about something which is called exponential function, which has a derivative equals to itself, right? Remember, if you differentiate e to the power of x, you are going to get back e to the power of x. Well, maybe a similar function can solve our differential equation. So what I'm going to do, I'm going to assume that my solution, y of t, is going to look like a constant a multiplied by e to the power of kt. Why did I choose to put k in front of argument t? Well, because I kind of know the solution, but actually you understand that if you differentiate something, you want to get a constant in front of the function, you just add a constant in front of x, and then differentiating the composition is going to produce this constant in front of exponential function. So basically, That was not like pure guess, but more educated guess. So now, guys, what I'm going to do, I'm going to differentiate this function and check if it fits into the equation. If it fits into the equation, I'm going to just assume that that's my solution. Well, there are more like stuff in this theorem, like proving that there are no other solutions, but we are not going to be concerned with this for right now. We are going to think about this when we move to differential equation class. So I'm going to differentiate this function, and I'm going to get L. That's a constant. I'm going to label A is a constant. And also we know that K is a constant, right? So derivative of exponential function is exponential function itself, and derivative of kt, if we consider t as a variable, is just k. Now I'm going to plug this derivative into my equation. So I'm going to plug it over here. I'm going to have a e to the power of kt multiplied by k equals k. And now over here, I'm going to plug in my original function, this one. A e to the power of kt. If I compare my left side and my right side, I'm going to see that basically it's the same expression, just with rearranged terms. A, E, E, K, K. So everything is here and everything is here. So actually, my equation is becoming a true statement. Means that this function solves actual equation. Well, again, we are not going to be concerned with like uniqueness of this solution, that there are no other solutions. For now, you will just trust me that there are no other solutions. So normally, guys, we are going to look for a solution in the form of y of t equals a e to the power of kt. We know about k, it's already going to be given by the equation. What is going to be a? Well, you know that depending on like what population you have initially and you start, it's going to end up with a different population at the end, right? If you start with one couple and like in 2 years you are going to have that many people, or like in 1 year you have 3 people, right? If you start with 4 people, 2 couples, you are going to end up with 6 at the end, right? 4 old people and 2 new people. So looks like something in my final function supposed to depend on original population of like whatever objects you consider, people or animals, bacteria, radioactive material. So I'm going to plug in t equals 0 into this equation, into this function. Y of 0 equals a e to the power of k multiplied by 0. Well, k multiplied by 0 is going to give me 0. E to the power of 0 is going to give me 1. So I have a multiplied by 1 or just a. So my constant a actually is going to be the value of my population when t is equal to 0. So now I'm going to rewrite my solution in terms of this knowledge that this is y of 0, initial population, and then e to the power of kt. Now, guys, when somebody gives me a population growth problem, I'm not going to solve differential equation again and again and again. I'm just going to use actually the ready solution for this. Okay? Well, now, guys, let's try to solve something. Okay? I'm going to consider a standard book problem with world population and prediction. And it's very typical problem for exponential growth and decay problems. So let's consider it. So the example, that's going to be example number 1 maybe. Existing world population in a year of 1950 is 2,560 million. So goes for millions of people. I don't want to write it in thousands. Just actually, if you kind of look at this number, like in terms of billions, it's 2.5 billions, right? In a year of 1960, the population is 3,040 millions. Increase of the population over 10 years. I'm going to put year, right? That's years. Let's assume that population growth exponentially. and estimate population, world population in, let me write down population, otherwise the problem doesn't sound kind of nice. Okay, sorry. Instead of writing down population, I'm writing down population. Population in 2020, kind of. I'm going to put comma, assuming exponential growth. I would say that, why do we kind of write it down? Assuming exponential growth. Because population not always grows exponentially. Well, in a simple example was like a one couple of or two couples. This is hypothetical example, but there are many other natural phenomena that affect population, not only the rate of growth. Well, there are, like, for example, some natural disasters, some wars, some pandemics. All kind of things can also decrease population. And normally, guys, population does not grow exactly exponential, but for a first estimation, we can assume exponential growth. And so I'm going to write down how population growth in this case is going to look. P of 0 e to the power of kt. What do we know? Well, we don't know what was population at the year of 0, but the beauty of the problem is that P of 0, well, or time equals 0, can be set at any kind of convenient time for us. Usually, guys, we consider time equals 0 as a first given instance of population. So at time equals 0, we are going to write down that population equals 2560. And that means that in 1960, which is 10 years away, at time equals 10, I'm going to just write down population of 10, and here maybe population of 0 equals 340. Now, we already know kind of initial population, and we just don't know what is a constant. So I'm going to write down that initial population, 3, sorry, my 5 looks like another 3 here, 5. So I'm going to just plug in the numbers. And assuming that the model is working, on this side, population after 10 years supposed to be, well, maybe I should write down the expression first and then plug in the numbers. I'm going to write down population after 10 years, starting with year 1950, is going to be population at 0 years, which is actually 1950, e to the power of k. And because the time passed from 1950 is 10 years, it's multiplied by 10. Now, what do I know here? I know P of 0, I know P of 10. I'm going to plug them in. 3, 0, 40. And over here, I'm going to plug in 2, 5, 60. E to the power of k multiplied by 10. What I have is actually exponential equation, right? We do know how to solve it. Let me show you how we usually solve this. I'm going to move this 2560 to the left side by dividing by 2560 here and 2560 here. So now I have 3040 divided by 2560 equals e to the power of k multiplied by 10. Now, guys, we need this k, but k sits as argument of exponential function. Usually, for example, if we have a square root of x equals to 4 and we need x, which is argument of the square root, we are applying inverse function. Let me kind of explain it briefly. Square root of x equals 4. We are applying inverse of a square root function, right? We square this side and we square actually this side, right? And like here we are going to get x, and here we are going to get 16. So actually square root of x equals 4 means that x was 16. Here, what is inverse of exponential function? That's a natural logarithm function, right? And that's what I'm going to apply in this case. Let me use a different color. So I'm going to put ln on this side and ln on this side. What is going to happen with ln and e when we apply them together? Remember cancellation rule for direct function and inverse function. They cancel each other and we are just going to get the argument. Our argument is k multiplied by 10. What we are going to have here? Here, we're just going to have a decimal number. If we plug it into our calculators, we're just going to get a number. I'm going to keep it as expression and then plug everything at the very end, 2560. Now, how do we calculate k? Well, we just need to divide by 10, right? Both sides dividing by 10, and, well, I'm going to put 1 over 10 here, but actually I'm dividing by 10, right? So my k, in this case, is going to be equal ln of 30402560 divided over 10. And I can actually plug everything into a calculator and calculate what is my k, which I kind of did ahead of time, and I calculated that my k is equal to 0.01718 approximately. There are more digits here, but approximately like 4 significant digits are 17, 18. Now, guys, I can write down the law of population growth as population of t equals, what is our population of 0? Let me go back. Population of 0, that's what I'm trying to rewrite. Population of 0 is 2560. I'm going to copy it. 2560 e to the power, and if I look back on my kt, k is equal to that strange number 0.01718, and over here I'm just going to put t. So this is my population growth function, right? Now I can answer the question of the problem, which is asking what is going to be population in the year of 2020. To do that, we'll need to know what is time here. Well, t equals 0 is actually a year of 1950. What is going to be t if the year is 2020? Well, we have like 50 here and 20 here, so actually we are going to have 70 years, right? Now we can just plug in this 70 instead of t and get the answer. So population at 70, which is going to be population actually at this 2020, 2020 is going to be 2560 e to the power of 0.0. Well, I should not keep the screen vertical when I'm recording. I guess I should just plate it horizontal. 1718 multiplied by 70. And we just plug everything into a calculator and get our final answer as 8524. And I'm going to keep millions, and I rounded this number to make it like nice looking. So what we actually solved in this problem. First, we found the rate of change, right? And second, we've predicted the population. Well, I think this prediction is a little bit too much for the current population, right? I think, but kind of good estimation, right? Okay, now it's time to move to negative case or radioactive decay. Okay. So, what kind of phenomenon is radioactive decay? Radioactive decay is decrease of like a material mass due spontaneously emitted radiation, or kind of breaking atoms into smaller parts. Actually, like all materials even like, I don't know, hydrogen or helium, are a little bit radioactive. But some of the materials are radioactive within like a few seconds and they spontaneously break. And some materials will need like 5 billions to spontaneously break. So all materials are radioactive, but some of them are radioactive faster. Let's kind of talk about like what how radioactive decay happens. Well, um, in radioactive decay, what we are going to have? We are going to have a mass of a sample. Mass of a sample. And usually it's going to change with time because some atoms are going to break. We are going to have m of 0 initial mass. What else? Also, we are going to have constant of decay, which is less than 0, because amount of material is going to decrease, and to create that, we will need to have a negative derivative, right? So I'm going to write down decay constant. In some books, you are going to have it labeled as R. It doesn't matter like which letter you use. I'm going to write down the equation of decay, which is going to look a lot like equation of population growth. So if you look at this equation, it's exactly the same as population growth. How do we know that something is going to decay from this equation? Remember that depending on the sign of argument, function is going to behave slightly different. I'm going to draw, as example, two exponential function. One is with positive argument, one with negative. So this is our standard exponential function, e to the power of x. And this one is going to be e to the power of negative x. You see that if you consider a moment time t equals 0, that was time amount of matter or like decaying object is going to decrease. Considering the population, which is growing exponentially, right? Well, for radioactive decay, we also have so-called half-life. Half-life is a time needed to decay half of the quantity or half of the mass which is given. So for example, somebody gives you 10 grams, how long it takes to get just 5 grams? Called half-life. Actually, for population growth, we also have something similar, but we are going to call it a double time, and population doubles. Especially this double time is important in the bacteria growth, like when amount of bacteria doubles. But, well, we just kind of going to stick to half-life. There is no special letter for half-life. So what I'm going to use, guys, for half-life, I'm going to use just T with index subindex 1/2, showing that this is half-life. Why I'm using T? Because actually half-life is a time needed to decay half of the material. 1/2, well, just because it's half. You can also see tau, letter tau, to label half-life, letter lambda to label half-life. You can label it as you like, just understand what you mean. Well, we are going to first talk about half-life and how it's connected to the decay constant. What is the connection between half-life and decay constant? Because equation is going to, which is looking like this, right? It doesn't have any half-life, it has a constant. But how half-life, which is usually given in a chemical table of like elements. If you look at the chemical table of elements, the fast radioactive materials usually are given half-life or time it takes to decay half of the material. Uh, well, let's kind of go back to the equation and write down m of t equals m of t0. I'm trying to write down m instead of writing down t0 e to the power of kt. Let's plug in over here half time of half-life. So m of t1 half is going to be equal m of 0 by e to the power of k t1 half. Here again, t is just the special time half-life. It's not like a square root of t or t multiplied by 1/2. And it's supposed to be equal to the half of initial population. My initial population is m of 0. Half of it is m of 0 over 2, right? I don't know initial population, but I know that after half-life, it's supposed to be down by 1/2. So now, guys, I will try to solve this equation, assuming that I do know half-life and kind of figure out what is k. As you see probably, both sides of my equation have this m of 0. I'm going to cancel it or divide by it. And my equation is going to become much simpler. E to the power of k t1 half equals just 1/2. Well, because I'll need to find k, I'm assuming that I know half-life. I'll need to take inverse of exponential function to get to this argument, right? Inverse of exponential function is a natural logarithm, so I'm using ln e k t1 half this side, and then just ln of 1 over 2 on this side. Now, guys, I'm going to cancel ln and e because of cancellation rule, and I'm going to get k by t1 half equals ln of 1/2. And now, guys, maybe this is going to be better formula to remember. You see that the decay constant multiplied by half-life equals ln of 1/2. What we can do here, guys, we can actually solve for k, and we are going to get k equals ln of 1 over 2 divided over t1 half. I'm going to work a little bit with ln of 1 over 2. Remember that when we have a fraction, that's actually ln of 1 minus ln of 2, right? We can kind of represent it as a difference of two ln's. And in our case, ln of 1, which is equal to 0, disappears, and I'm going to get expression minus ln of 2 by t1 half. So my constant is actually negative, physically negative. This is positive number, this is positive number, so we are going to have physically negative constant. Remember, I was telling you that constant over here is negative. Sometimes in the book, you are going to have explicitly minus in front of this constant. That's okay. Just understand that then if you put minus there, the constant itself must be positive. But if you don't put minus, then your constant is going to be just numerically negative. Okay? So you can remember also this equation if you kind of like it more. So constant is equal negative ln of 2 divided over half-life. Now we can solve some equations using this knowledge. So let me set example number 2. That's a typical example for radioactive decay. Half-life of radium 226. Half-life of radium. And guys, in problems like this, radium 226, it's a name of radioactive material. So there are different radiums with different mass over here. And for this one, we do know half-life, and it's going to be equal 1,560 years. So this 226 is not part of the problem. That's just a name of the material. Just there are different radiums with different mass, and one of them is going to have mass of 226. Okay? Or so the label for isotope. Now, the initial mass given M0 is equal 100 milligram. And the question is when the mass of radium is going to be reduced to 30 milligrams. When means that how long we need to do that. Okay, let's try to solve it. Well, what I'm going to do, guys, first I'm going to start with writing the decay law. M0 e to the power of kt. And because I do know half-life, which is going to be T1 half, and I remember my formula, from the formula I know that actually constant is going to be equal minus ln of 2 divided over 1560. That's what I'm going to plug into my equation. So M0 is 100, right? E minus ln of 2, 1560 T. So basically this is how its mass of the element is going to decrease with time. Now the question is, when the mass is 30 milligrams. So what we know? We know the final mass. Mass is 30 milligrams. We don't know the time, so we are going to solve it for the time. So 30 equals 100 e minus ln of 2, 1560 t. You see, we got equation with one unknown, which is time, but this unknown is hidden under exponential function. I'm going to start with clearing exponential function from this 100. I cannot take ln of both sides over here just because exponential function right now is mixed in the product with 100. But if you divide both sides by 100, canceling 100 here, you can take ln. So ln 30 divided by 100 is going to be 0.03, right? So not too many zeros actually. It's supposed to be 0.3, and I put 2 zeros. And on this side, ln of exponential function is going to cancel, and I'm going to just get ln of 2. 1560 multiplied by time. Now, that's just linear equation. It looks a little bit weird because my linear equation has two ln's, but ln's, we remember, they are just numbers. Like a square root of something is just a decimal number. So what I'm going to do, guys, to calculate t, I'll need to divide by this expression both sides of the equation. So that's what I'm going to do. ln of 0.3 divided over ln of 2, 1560 with minus is going to give me my time. Now I just need to plug everything into a calculator and get time. And you probably will tell me, okay, we do have a obviously minus here. Is time going to be negative? Well, no, because actually the top of my expression is also negative. Remember that ln, let me remind you how ln looks. ln looks like this, right? That's ln of x. And here is 1. So when argument is 0.3, it's somewhere here, and the value of a function is going to be negative. Okay? So let's plug everything into a calculator and try to find out what is going to be the answer. So let's imagine that I did the plugging in, and after calculating, I'm going to get t equals 2,762 years. So I rounded this answer to the whole amount of years. Well, kind of a little bit more than like one half-life, right? Guys, when you solve problems with population growth and decay, make sure that you kind of check your answer with common sense. We know that in 1,560 years, about half of the elements supposed to decay. Half is 50, right? So 50 milligrams is going to happen after 1,500 years. And like we do need 30, which is almost half of the half. So we need extra time. And that my number is matching the idea that it's going to be a longer time. Okay, So that was a typical problem of exponential decay. Let me just kind of make it smaller and scroll it down to show you the whole problem. Um, and well, you can have slightly different questions, and maybe they'll give you a constant and ask about half-life, or they'll give you initial and final values of the element and they'll ask about like a constant. But usually it's going to be reduced to equation with one variable. Okay. Okay, the last type of problems which are dealing with exponential growth are continuously compounded interest problems. Um, well, I'm going to like explain a little bit how the problems is ending over there because it kind of looks different, right? The decaying matter and growing population and how this continuously compounded interest is appearing over here. So I'm going to start with setting a problem continuously. Oh, my. Uh, compounded interest. My Y doesn't look very good. Okay. Well, I'm going to start with setting a problem. I'm going to set investment problem. Let's invest amount A, amount of money, which is going to be $1,000 at 6% annual interest. Well, there are several ways you can do this investment. The first way it's called a simple interest. Simple interest means that after 1 year, somebody is going to multiply this amount by 6%, get extra amount, add it over here, and that's going to be your final amount. So I'm going to write down A after 1 year. After 1 year will be original amount plus original amount multiplied by 6%. I'm converting 6% into parts of 6%, because actually percent means divide by 100. I'm going to simplify a little bit this expression by taking 1,000 outside. And here I'm going to have 1 plus 0.06. I'm going to write it down as a more general formula. I'm going to write down A0, original interest, original amount, here 1, and here instead of the 0.06, I'm going to write down R, interest rate. Okay? So I'm going to label this 0.06 as interest rate. Now, what is going to happen after 2 years if we continue doing that? Well, after 2 years, you are going to have, I'm going to just kind of write down 2, and we are going to have initial amount of money, right? And we are just going to multiply it by parentheses because like 2 years is just like 1 year after 1 year, right? So this is just new initial, and we multiply it by this parentheses, 1 plus R. So initial multiplied by parentheses, new initial multiplied by parentheses. We are going to have the very, very old initial multiplied by 2 parentheses. So it looks like the amount of years is going to be a power of parentheses. So if you want to calculate amount of money after 10 years or after T years, you are going to have a 0, 1 plus R to the power of T. After T years, 10 years, 15 years, you just have that many parentheses. Okay, now, what can kind of be different over here? Well, actually you can compound the interest several times a year, not like annually. But like, sorry, I should write down annually here because that's not annual interest, but that's interest compounded annually. But so what if you decide, well, I'm going to actually do the interest twice a year. Twice a year means that first half a year I'm going to calculate 3% of the sum, and the second half a year I'm going to do another 3% of what happened after the first half of the year. Well, then the formula is going to change a little bit. So if we calculate the interest n times a year, sorry, what is going to happen? Well, I'm going to write down a after 2 years again. So generally speaking, when we do calculation of interest, we multiply by 1 plus interest rate, right? Because we calculated n times a year, my interest rate is going to be rate over n now. For example, if you calculate it twice a year, so it's not going to be 6%, but it's going to be 3%. So I'm going to put 1 plus r over n here. Now, if you calculate it more than once a year, like twice a year, then amount of this parenthesis is going to be twice more. Like after 1 year, you not multiply only by 1 plus r, but you are going to multiply 1 plus r over 2 and 1 plus r over 2 because you are doing it like twice a year, right? So if you do it n times a year, you are going to have amount of years multiplied by n, something like this. And that's going to be a new formula, right? So n here can be equal to 2, for example. You calculate it semi-annually, or 4, you calculate it quarterly, or it can be equal 12, you calculate it monthly, or it can be 365, you calculate it daily, or n can go to infinity. You calculate it every millisecond. Let's consider this case. And this case is called continuously. Continuously means that you never stop calculating the amount of money. Well, you remember that when something approaches infinity, we consider a limit. That's what I'm going to do, guys. I'm going to consider a limit. I'm going to put this expression under the limit. A0, it's initial amount of money. And you guys already probably kind of see something familiar in this formula. Limit as n approaches infinity. Well, guys, what are we going to have when n approaches infinity? In parentheses, we are going to have some number, percent rate, and usually it's not a big percent rate, divided by infinity, which is going to be almost 0. And in the power, we are going to have infinity, right? Remember, we had a similar limit in the previous section. I'm going to do over here a little substitution to make it more similar to the limit we had the previous section. So what I'm going to do, guys, I'm going to label this expression as x. Then what should I write down instead of here? Well, if this expression is x, what I'm going to have for n over here, let's calculate. X equals r over n, from where n equals r over x, right? So just like I put n here and put x here, like exchange them. I'm going to copy this expression, limit as n approaches infinity, and that's going to be a0, 1 plus x. And over here, instead of n, I'm going to put r over x multiplied by t. Now, guys, in my limit, I don't have any n, so I have to do something with this n. So when n approaches infinity, my x, which is going to be my new variable, right? Because it's a substitution, is going to approach 0, right? So I'm going to change it to 0. So I'm going to cross this and write down x approaches 0. Well, just because when n approaches infinity, if I create x by this formula, it will approach 0. So guys, you probably will recognize our special limit, right? Let me remind you how it was looking. Our special limit was looking like this. 1 plus x, 1 over x approaches 0, and it was equal to what? E, right? So uh, let's kind of use it, right? What do we need to use it? What do we need to do? Well, I'm going to copy everything, but I'm going to take this a0. Maybe I should put it in front of the limit so it's not going to bother us. A0 outside of the limit. What I'm going to keep inside of the limit? 1 plus x and 1 over x, and then I raise it to the power of RT. Why? I'm going to represent this power as 1 over x multiplied by RT. Well, t is a numerator, r is a numerator, I can always do this. I remember that when I have the product of powers, it's actually power in a power, right? Well, for this limit, I already know that it's going to be e, right? This limit is e. So my final answer here, sorry, my line is too long, is going to be a0 e to the power of rt. Wow, which is also a population growth formula, right? Just if you label r as a like k, that's going to be e to the power of kt. So we got a brand new formula. So the growth of money with time, if you calculate your interest continuously, is going to use the very same formula as population growth. Well, let's kind of try to solve a problem. Example 3. Well, imagine somebody invests an original amount of money of $1,000 and the time is going to be 3 years and the rate of growth or annual percentage rate is 6%, which is actually what? 0.06 for our equation. And the interest is calculated continuously. Continuously calculated interest, which means that we have to use this formula. What is going to be amount after 3 years? Well, let's put a at 3 equals a0, 1000, right? I'm just writing down. Then e, my rate is 0.06 and my t is equal to 3. Well, I'm just going to plug everything in and use my calculator. If I multiply this by 3, I'm going to get 0.10. And if I plug it into my calculator, I'm going to get 1,197.22 cents. That's the amount of money I'm going to have after 3 years if I invested under 6% and combine my interest continuously. Well, not like much more, but continuously compounded interest is the fastest growing interest. So if you calculate it once a year, you are going to have a smaller amount. Okay, I think that's all the theory. Now I'm going to just give you a problem to solve. Guys, there are not too many different problems we can kind of have for this section. So my suggestion is to do the homework and practice on the next problem by the next class. And that's just one problem. I'm not going to give you like 3 different problems which are going to use the same formula. So the problem is going to be like this. Bismuth 210. Again, this is a name of the element. This is not time or not half-life or anything. Has half-life of 5.0 days. A sample has mass equals 900 milligram. Find the formula for the mass remaining after T days. Second question, when the mass is reduced to 9 milligrams. So when the mass is going to be reduced 100 times. After how many days? Well, you see, bismuth is fast decaying element. Only 5 days takes to decay half of it. So it's 909. And the half-life is 5. 3 essential numbers. If it's kind of hard to read what we have. Okay, that's it. And I'll see you Wednesday.